thank everybody for attending. We really appreciate it. We have people from, I think, as many as 15 countries. And at last count, 230 or 250 registrants. So really a very strong showing. The presentation today will be delivered by Eduardo Laje, who is the Chief Technical Officer, the co-founder of PlenOptika, and also a professor at the University Autónoma of Madrid. And he will be reviewing the presentation and answering any questions you have. As I've mentioned in the chat, kindly submit your questions via the Q&A function. We will try to answer as many as we can. The webinar will be recorded, and as soon as we finish the recording, everybody that's participating will receive a copy of the recorded webinar. This will also be sent to the distributors so that they can also forward it. So again, if you do have a question, please submit it in the Q&A. And with that, I will hand it over to Eduardo, who's going to start the presentation right now. Thank you, Eduardo.
Thank you very much, Oscar, and thanks to everyone for joining this webinar in which we are going to present our flagship product, the QuickSee, which is the world's most accurate handheld refractor. Okay, as Oscar has mentioned, apart from being the CTO of PlenOptika, I am a professor in one of the biggest universities of Spain. And the title of the presentation is Performing Accurate Auto-Refraction Anywhere. Well, where are we coming from? So PlenOptika is a spin-off of Massachusetts Institute of Technology, and it was funded by innovation experts in medical imaging. We introduced our device commercially in 2019, and since that date, we have sold more than 2,000 devices. And somebody can think that this is a small quantity, but in fact, if you think about this date in which the COVID pandemic started, it's a huge number, taking into account the situation. What are the main characteristics of the product? So the product is approved by the FDA, is registered with the FDA. We have CE marking, and we have more than 40 distributors all over the world, covering more than 45 countries. The technology is a completely innovative technology, and we have service centers in the United States and Europe with local support. In terms of global impact, we have tested the device in more than 4 million patients. As I mentioned, we are covering more than 45 countries, and the device has been validated in several clinical studies, as I will describe by the end of the presentation. What are the basic features of this product? Well, the first thing that I want to call your attention is that this device doesn't have the typical shape of an auto-refractor or even a portable auto-refractor. We have a binocular form factor, but we can perform binocular or monocular eye measurements. Each measurement takes around 10 seconds, plus the alignment time. So the alignment is usually very simple and should not take more than 1 minute. With an experienced user, alignment is immediate. It can take something like 10 seconds. It is powered by an internal battery that has 6 to 8 hours battery life, and this obviously depends on the usage. If I am testing patients all the time, the battery will last less time. And the weight of the device is 1.5 kilograms with a case, so in fact it's 1.375 kilograms. It's calibration free. It arrives to you perfectly calibrated, and you don't need to care about the calibration of the device. About the training time, so basic instructions can be provided to the operator in 2 minutes, but with a 1 hour training time is more than enough for any kind of use. Regarding the technical information, so we have an interpupillary distance range from 47 to 78 millimeters in continuous mode, and this is important because, as I have mentioned, this is a binocular device and it is possible to perform binocular measurements. The spherical range goes from plus to minus 10 diopters, and the cylindrical range from plus to minus 6 diopters of cylinder. We can measure pupils as small as 2 millimeters with this device. But what is making this technology unique? Why the results are so accurate? Well, it's a combination of factors. The first of them is that the device is open view. When we are measuring a patient, the patient is looking through the device, not looking into the device. And this is important because if a patient is looking into a device, sometimes there is induced myopia. If the device is open view, like the QuickSee, this relaxes patient's accommodation during the measurement to collect better quality data. Apart from that, and in order to mimic a natural viewing experience, the device is binocular and can measure the patient while the patient is looking through the device at a distant target. Okay, it's a natural viewing experience. And the fact that this device is binocular, we have tested that can reduce anisometropia during measurements. The third factor is that the device is using wavefront aberrometry, which is the most advanced technique for measuring refraction. In fact, wavefront aberrometry is the technology that we use to plan LASIK surgery. Okay? Finally, the device acquires in video mode. What is the difference with the standard auto-refractors? In a standard auto-refractor, basically, you are taking some snapshots of the refractive error of the patient and doing an average. In our case, we are acquiring in video mode. So for each measurement, we acquire a sequence of refractions that are correlated in time. And we are analyzing this dynamic data to improve the data of the filtering analysis. This combination of factors, or this unique combination of design factors, make QuickSee the most accurate handheld auto-refractor in the world. What are the steps that we need to perform in order to do an exam? So first, we start with a pre-alignment step. The eye cap of the device is attached to the device with magnets and can be easily detached. In the eye cap, we have some rulers or indications that allow us to estimate the pupillary distance of the patient. In order to do so, we just need to ask the patient to place the eye cap in their face, and we can very easily estimate the PD just looking at the numbers. After that, we attach the eye cap again to the device, and we pre-adjust an IPD wheel that we have on top side of the device in order to match the position of the device with the interpupillary distance of the patient we want to measure. At this point, we will press OU in the screen if we want to measure the two eyes simultaneously, or either OD or OS if we want to measure a single eye. At this point, we will see the device interface in which the viewports are represented by the small circles, and the eyes of the patient are represented by the big circles. And we will see that the small circles are close or inside the big circles. Just by moving a little bit the thumb wheel, we can do a fine-tuning. And whenever the patient is aligned with the device, we will see that the interface turns green. Both eyes or only one eye, just to guide the operator during the alignment process. Once the interface is green, we can press the play button at any time, and in 10 seconds, we will have the measurement. After the measurement has finished, we will see the results in the display of the device. And the device will be showing the typical results: sphere, cylinder, axis, and spherical equivalent for the left eye and for the right eye. We can repeat the test as many times as we want, either binocularly or monocularly. How is the user interface of the device? So we have put a lot of effort in making a friendly and easy to use user interface. So basically, we have very few controls in the main screen. We have this button, which allows us to access the menu of the device, in which we can see the patient log, we can adjust the settings, we can see the help, or we can power off the device. There is a label which indicates the patient number, in this case 146, and the main buttons are these ones in the middle of the display, The central one allows us to measure both eyes simultaneously, and OD and OS allows us to measure either the right eye or the left eye, respectively. Also, we have other indicators in the device indicating, for example, date and time, and also the percentage of battery that is remaining in the device. After the acquisition has finished, the main screen is going to show the results, okay? The results for the measurement that we just did. If we have performed more than one measurement of each eye or in both eyes, we can measure or we can move from test to test using these arrows. And also, in case that we can provide the near vision addition, we can press this button and it will be shown a power chart indicating what is the addition that we need for any specific patient as a function of their age. Also, we can press any of these buttons that allow us to save or add a new patient. We can press this one to see some extra patient information that we have included in the device. We can repeat the measurements, or we can print the results using a standard thermal printer as in any other auto-refractor. So before continuing, let me play a small video on how the device is used. Okay, so I'm going to play this only 30 seconds. After this small video that is basically showing the use case or how to use the device, is no more than that. We are going to talk a little bit about the underlying technology that we have been using for the QuickSee. We are going to talk a little bit about wavefront aberrometry, that, as I mentioned, is the most accurate technique that we have nowadays for measuring refractive errors. How does it work? Okay, everything starts by projecting a small point of light in the retina of the patient. In this case, what we are doing is using a very low power laser source. When this point is projected into the retina, what is going to happen is that this light is going to be reflected from the retina as a wavefront, and it's going to pass through the optical system of the eye. That comprises the lens and the cornea. If the patient has no refractive error, after passing through the optical system of the eye, the wavefront is going to be completely flat. In the device, we have what is called a Harman-Schach sensor. This sensor uses a small array of lenses and a CCD camera. If the wavefront is flat, each of these small lenses is going to project a spot of light exactly at the focal length of the lens. So the result that we are going to see in the camera is a spot diagram in which the spots are perfectly aligned, or in other words, are in the exact position in which we will be expecting them. But what happens when we do this testing with an eye that has refractive error? In this case, the wavefront is going to go out from the optical system of the eye with aberrations, with deformations. These deformations are going to be captured by the lens array and the camera, and what's going to be the result? The spots that in the previous case appear exactly at the position in which we were expecting them now are going to be moved. So there is a distortion in the points. Well, by measuring the movement of the points with respect to a perfect eye, it is possible to reconstruct this wavefront. If we have this wavefront reconstructed, it's completely trivial mathematically to characterize in a perfect way the optical system that has aberrated the wavefront. If we have characterized this optical system, we have the refractive errors characterized to a level that is more than enough to provide eyeglass to the patient. we are measuring not only the low order aberrations, which is the information that we need for providing eyeglasses, but also the high order ocular aberrations that in this case allows us to refine a little bit the eyeglass prescription. In monocular mode, it is when we are measuring a single eye of the patient, the QuickSee can show the spot diagram. And this is important because for a trained eye, the spot diagram is providing a lot of information. Well, by default, even if we are measuring in monocular mode, the device is going to show the default screen in which we are showing a simplified view in which, as I mentioned, the circle, the big circle represents the eye of the patient and the small circle represents the position of the viewport. Okay. At any point, we have a toggle that allows us to switch between the simplified view or the spot diagram view. I'm going to show a video just to demonstrate how this works. Okay, so we start with the simplified view, but at any point we can press the toggle. Okay, and go to a spot diagram mode. In this case, we are seeing the spot diagram of the patient. In this case, we are starting the measurement. Even if we are in a spot diagram, the interface is going to show the main circle in green when the patient is aligned with the device. Why is important or why is useful to look at the spot diagrams? Well, as I mentioned, for a trained eye, the spot diagram has a lot of information. For example, an emmetropic eye will look like this, in which all the spots has similar brightness and the distance between the spots is very homogeneous. So we don't see a lot of distortion. And this is very easy to see when you have looked at several patients. For example, if the patient has myopia, the wavefront that is emerging from the optical system of the eye will be converging. And what we are seeing is smaller spot diagrams with bigger spots. In the case of hyperopia, we are in the opposite situation. In this case, the wavefront will be opening when it goes out. It will be diverging when it goes out from the optical system of the eye. So what we are going to say, what we are going to see is that the wavefront is expanding and the spots are smaller and smaller in this case. In the case of astigmatism, what we are going to see is that the spot diagram is aligned around one axis. In this case, the axis is more or less at 45 degrees. Obviously, this is going to change as a function of the magnitude of the astigmatism. In other case, for example, if the patient has opacities in the cornea, such as a cataract, we are going to see areas of the spot diagram in which the spots are not so bright. Okay, and this is very easy to detect small cataracts in some of the patients. In patients with keratoconus, the spot diagram can change a lot. So in some cases, in patients with advanced keratoconus, the spot diagram doesn't appear to have spots. So when we have a patient with keratoconus and we look at the spot diagram, it's like night and day. So we see it very clearly in the spot diagram. Also, some other special situations like a corneal scar or some other cases will create a very specific spot diagram that will be showing us that there is something strange with this patient. This is for information purposes only, not for diagnosis. The value of looking at the spot diagram can help us to determine what is the next test that we need for this patient. What are the applications? Well, we have mapped out the different sectors in which we are working now with our device. And in here, we have the main of them. So for example, in the clinic, in an ophthalmology or optometry clinic, the QuickSee is used directly on the subjective refraction chair to improve efficiency. So we don't need extra space for a desktop auto-refractor. The device has a small form factor and can be directly used on the subjective refraction chair. In general, doctors are buying the QuickSee as a second auto-refractor because it provides a lot of flexibility. For example, it allows to go to anywhere the patient is in order to treat him. or to check its refraction. In optical stores, it reduces the patient examination times by performing baseline auto-refraction either in the sales room or directly on the subject refraction chair. Some of our customers use the QuickSee as a sales tool. What is the procedure in this case? So we measure the baseline refraction with the QuickSee and use a lensometer on the glasses to check what is the refraction. If the refractions are different, we can show customer that they need a new pair of glasses. Okay, and this is a very easy way of using the device in order to increase sales. We have a lot of customers also that perform mobile eye testing. Basically, because of the fact that the device is designed to be used anywhere, it doesn't matter about the lighting conditions. Is it possible to use the device indoors, outdoors? Can be used by non-technical personnel. It has several possibilities. For example, QuickSee is used by many NGOs globally in vision screening programs. Let's go with the clinical validation. So far, we have performed a lot of different clinical trials, and these clinical trials has been performed not only in our site, I mean, not only by PlenOptika, but also by a lot of different independent researchers. And now there are several publications indicating the accuracy, the performance, and all the evaluation of the QuickSee in different use case scenarios. I'm going to talk about a few of them that are interesting. The first one is called Validation of an Affordable Handheld Wavefront Auto-Refractor that was published by our team in Optometry and Vision Science in 2019. How was the study designed? So basically, we wanted to characterize the performance of the QuickSee in an adult population. What were the methods? So basically, we measure the patients of this study with the QuickSee, with a desktop auto-refractor, and with subjective refraction, and compare the results. So we were comparing the results of the QuickSee versus the desktop auto-refractor and versus subjective refraction. In this case, we test a total of 55 patients with an age range from 22 to 65, and with a refractive error range from minus 7.25 diopters to 4.25 diopters of hyperopia. What were the results? First, we compare for which percentage of patients the differences between the auto-refraction and subjective refraction were smaller or equal than 0.5 diopters, or spherical equivalent. The desktop auto-refractor, in this case an IDEC ARK1, had differences smaller or equal than 0.5 diopters in 83% of the patients, while our QuickSee has differences smaller or equal than 0.5 diopter in 87% of the patients. What is the conclusion? So agreement between the QuickSee and subjective refraction is comparable, in this case better, than that achieved by last generation desktop auto-refractors. Apart from that, we compare the visual acuity provided by the prescription provided by the QuickSee alone versus the visual acuity achieved by subjective refraction. What we see is that with subjective refraction, we provide visual acuity of 20/20 to 83.6% of the patients. And with the QuickSee itself, this number was almost 75%. But the important thing is that the differences were minimal. If we increase the threshold of visual acuity to 20/25, just a little bit, a few letters, the numbers are exactly the same. 92.5% of the patients were able to achieve visual acuity of 20/25 with both subjective refraction and with the QuickSee. So the conclusion in here is also very easy. The visual acuity achieved by QuickSee refraction was bigger or was equal or better to that achieved by subjective refraction in 87% of the cases. and the average difference between visual acuities was less than 1 letter. The second clinical study I would like to describe is called Assessment of the QuickSee Waveform Auto-Refractor for Characterizing Refractive Errors in School-Age Children. In this case, the paper was published in 2020 in PLOS ONE. The study design is very similar to the previous one, but in this case, we use children. In this case, the age range was from 5 to 16 years, and there is another difference. That is that in this case, we have two different groups. One of the groups had cycloplegia, and the other group didn't have cycloplegia. Okay, so in the group with cycloplegia, we have 62 patients, and in the group with cycloplegia, we have 61 patients. Again, in order to characterize the performance of the device, we compare the results of the QuickSee versus a desktop auto-refractor versus subjective refraction. First, the results against the auto-refractor, in this case, a Topcon KR 8800. Differences within 0.5 diopter threshold. For the non-cycloplegic group, 61% of the patients were within that threshold, and for the cycloplegic group, 77% of the patients were within that threshold. For the QuickSee, first we see that the numbers for the two groups, non-cycloplegic and cycloplegic, are pretty similar, which is indicating that the open view design of the device is working in relaxing the accommodation, in this case, of the kids. And the numbers that we obtained were very similar, a little bit better for the non-cycloplegic group and a little bit worse for the cycloplegic group. Again, the conclusion is the same. The agreement between the QuickSee and subjective refraction is comparable to that achieved by last generation desktop auto-refractors. Okay, and I will keep this number. So we are 10% better with non-cycloplegic patients. And please remember that we are talking about children, and refractive children is always challenging. In terms of visual acuity, I'm just going to focus directly in the numbers that we achieved for the 2025 threshold. And we can see that the numbers, again, are very similar. Obviously, in this case, smaller than that achieved by subjective refraction, but still comparable. For the non-cycloplegic group, subjective refraction provide visual acuity of 2025 to 97% of the patient, while the QuickSee provide this number to 93% of the patient. For the cycloplegic group, the subjective refraction achieved 2025 or better, or not, 2025 in 95% of the patient, while the QuickSee was able to do the same in 88% of the patient, which is a number better than good, I would say. So the conclusion again is quite similar. The visual acuity provided by QuickSee was equal or better than that achieved by subjective refraction in 77% of the patients for the non-cycloplegic group and in 74% of the patients for the cycloplegic group. Well, I'm going to focus in this last study that was published in the top journal in ophthalmology, in this case the name is Ophthalmology, and this is a very interesting research paper in which we investigate the accuracy of the device, but in this case to provide eyeglasses without subjective refraction. How is the study designed in this case? So the research question is it possible to use QuickSee directly to prescribe eyeglasses? This may sound not reasonable for some of you, but just think in developing countries in which there is no optometrists, there is no eye care professionals, there is no facilities for dispensing eyeglasses. So in this situation, this is an option that the science is telling that it is starting to be worth considering. Okay, so basically, what did we do? What did we do in order to answer this question? What we did during this study is we tested a lot of patients, and we used QuickSee to obtain the refraction, and also we obtained subjective refraction from an experienced optometrist. After we have these two refractions, we created two pairs of eyeglasses, one with the subjective refraction and the other one with the QuickSee refraction. And what we did is to provide in a random order these glasses, these two pair of glasses to the patients in order for them to wear them for 1 week. Okay, so patients were wearing the first pair of eyeglasses during 1 week, and at the next week, they were wearing the second pair of eyeglasses. At the end of these 2 weeks, we asked the patients to tell us, okay, which pair of eyeglasses do you prefer? Well, in this case, we tested 300 patients. All of them were adults. The average age was 28.4 years, and the age range was from 18 to 40 years. The results were really surprising. So 50.5% of the patients, which is 152, prefer subjective refraction. 49.5% of the patients, which is 149, 3 patients less, prefer QuickSee. And what is telling us this result? So basically, this result is telling us that there was no preference for the refractions provided either by the QuickSee or the subjective refraction. It's important to say that in this study, there was a strong agreement between the QuickSee and subjective refraction. So the starting point is that the refractions taken by the QuickSee and the optometrist were very similar. And there was no statistically significant difference in the preference, which is the very important result that we have achieved in this study. These results support the use of QuickSee to prescribe eyeglasses in settings with no eye care professionals. Okay, this is what we have been defending in this study. Well, apart from these 3 studies that I have commented, which are from PlenOptika team and some very close collaborators, there are several independent studies comparing our technology with other established handheld or portable auto-refractor. For example, this one published in PLOS ONE by a team of Harvard University. They were comparing our QuickSee with the RetinoMax and with the Inetra. This study and most of the others are open, so are free to read. But so I just take some paragraph, just that I think that are very illustrative of the results. In this case, the QuickSee device is also significantly less expensive than the RetinoMax, about 60 to 75% less based on the US retail prices, depending at the time of this reading, had a short learning curve for both practitioners and subjects, and had the most accurate measurements of the 3 handheld devices tested. Okay, this was a study with a few hundred of patients, just in case. There is another recent paper published in 2020, which is called Better 1 or 2, a systematic review of portable automated refractors. And in this case, the authors were comparing the Smart Vision 1, Inetra, RetinoMax, and QuickSee. Again, I just took a paragraph just to summarize the results. There were 4 portable auto-refractors: Inetra, QuickSee, RetinoMax, and Smart Vision 1, studied against subjective refraction. There was high patient acceptance of glasses prescriptions by the QuickSee alone, with 87% of subjects saying the same or better than subjective refraction. QuickSee was more accurate than Inetra and RetinoMax. The last study I'm going to mention was published in 2021 in Translational Vision Science and Technology, and the title of the study is "Does the accuracy and repeatability of refractive error estimates depend on the measurement principle of auto-refractors?" Again, I'm just taking a paragraph, in this case on the conclusion section of the abstract, that says, refractive errors measured using auto-refractors operating on different principles show minimal bias and good certain repeatability, but relatively large agreement limits, vis-a-vis retinoscopy. Among them, the wavefront aberrometry base EC, this is our device, but in India and surrounding countries, we are selling with this name. The EC auto-refractor performs relatively better in all measurement parameters evaluated here. Well, after reviewing these publications, I just would like to finish with a quick summary about the features of our QuickSee. Handheld with Auto-Refractors that allows for field, clinic, and optical store use. It has shown in every single publication or clinical trial a very strong agreement with subjective refraction. So it's able to provide clinical quality measurements on the spot. It's convenient and really easy to use. In 1 hour training, you can become an expert. It's robust for portable use. There is no problem with lighting condition, as it is the case with several devices, especially with photo screeners like the Spot. It can be used indoor, outdoor, and doesn't need calibration at all. And finally, is competitively priced. Please discuss with our local distributor about this topic. And just to finish, I would like to thank all of you and give a special thanks to our distributors, Mr. Karen Mitano from Kenya, Medical Assistant Nationals, Mr. Eddie Gerges from the Middle East region, Mr. Hassan Margui from Morocco, Don Antonio Farello from Portugal, and Mr. Creightil from the Southern Africa region. Thank you very much.
Thank you, Eduardo. I really appreciate it. I have a series of questions that have been submitted, so I'm going to give them to you. The first question was a question about using the device for hypertourism. Can you hear me, Eduardo? You're on mute. I think you might need to leave your deck, your slides up. When you signed out, it cut you off.
Hello, Oscar.
Ahora te oigo. I can hear
I
you.
cannot hear you for some reason.
Can you hear me? Okay, I will send the questions on chat. Can you not hear me, Eduardo?
I can hear you. I can hear you now.
Okay, the question was about hypertourism.
Yeah, can you tell me the specific question, please?
Does it work in cases of hypertourism?
So basically, the range of measurement of the device is what I have described. It goes from plus minus 10 diopters for a sphere and plus minus 6 diopter for astigmatism. If the patient is within that range, the device should work properly. Okay. That will be the only constraint that we have from a technical point of view in that sense.
Okay. The other question is, what will be the readout if you go beyond that range?
So if you go beyond that range, so it's going to tell you the device is, or sorry, the patient is out of the myopic or hyperopic range, which is telling you that the patient has more than 10 diopters of myopia or hyperopia, or in the case of astigmatism bigger than the one we can measure, the device will show you a message telling that the patient is outside of the sphere or the cylinder range. That is giving you additional information. So your patient is more than 10 diopters of either myopia or hyperopia, which is the usual case. So usually you are going to see this message very little. We have checked with that the measurement range we have we are covering roughly 95% of the population. It's very strange to see somebody with more than 6 diopters of hyperopia, but it's not so strange to find somebody with 12 diopters of myopia. In those cases, the device will be telling you is outside the myopia range. That is telling you that the patient has more than 10 diopters of myopia. That will be the result.
Okay, thank you. What about the overcorrection for myopic patients?
Overcorrection.
Yes.
Well, so in any auto-refraction device, there is always a possibility that the patient accommodates during the measurement. Okay, if the patient accommodates during the measurement, the result is going to be more myopic than it should be. Okay, so in those cases, there may be a mistake, but the device is specifically designed to deal with this issue. How is dealing with this issue? With the open view design and also recording in video mode. Why recording in video mode is helping in this sense? Well, accommodation usually is a dynamic process, or it's always a dynamic process. And that means that accommodation or the focusing power is changing a long time. Since we are measuring in video mode, if the patient accommodates during the measurement, we are going to detect it and correct for that. So we are limiting the overcorrection of myopic patients in this way. It's a combination of the video mode and also the accommodation relaxation because the system is open view. Is this perfect? No, there are no perfect devices, but we are using the best possible approach that the technology can provide.
Thank you. Okay. There's been several questions about the use of the device in children and also the weight, recommendations on how to use it in children, kind of the limitations, etc.
Well, regarding the weight of the device, is 1.3, 1.4 kilograms. Okay, it's not exactly 1.5. And the measurement time is 10 seconds after we align. So sometimes what we do with small children is we help them just holding the device on the back side. Okay, we align the device, we hold it with our hands, and we also put the hand, the operator put the hand under the device just to help the children during the measurement. We can do the same if the patient is in a wheelchair or has some kind of disability. This is the standard way we work.
Okay, thank you. What about the calibration? How is the device calibrated, and does it require calibration in the field?
Well, we have managed to include all our technology in a single and well-encapsulated optical channel. We have 2 optical channels in a QuickSee, one for each eye. And once this is encapsulated and validated in our factory, that never moves. Okay, so the optical components are not moving. There is no moving optical components as it is the case in standard desktop auto-refractors. And this is the case, or this is the reason, because after we finish assembly and manufacturing of the device, there is no extra calibration step required because everything is perfectly enclosed and there is no internal moving parts.
Yeah, and you don't need to calibrate for different ages or in the field. It's basically calibrated in the factory. If there's a problem in the measurement, the device will tell you, and at that point, it needs to come back to the distributor for factory recalibration.
It's just that. It's just that. But usually, even when it comes to factory, so if the problem, so usually there is no problem with the optical channel. So the typical things that we have to do is to replace a battery or things like that. If there is no problem with the optical system obviously can be damaged if the device drops down. But even in those cases, we have been servicing devices that has been dropped down in which we didn't need to recalibrate absolutely anything. The optical channel was still working.
Okay. There's been a question about how we actually do the measurement. It looks like there's a user that has a device and is unclear about why we have a red dot in the device and that it's somewhat confusing.
Well, so during the measurement, the typical thing we do is, as I mentioned, we start providing the ICAP to the patient, so we have an estimate of the IPD of this patient. Okay, we place again the ICAP in the device and we pre-adjust the IPD wheel to the position or to the distance that we have estimated. At that point, the typical thing is that the operator asks the patient to take the device with his hands and align it to his or her face. Okay. The patient is going to be seeing two small red spots. Those red spots are the laser that we use in the wavefront aberrometer. Okay, one spot for each eye. In the user interface, we are going to see the position of the eyes of the patient, which is indicated by the big circles, and the position of the optical channels. The optical channels will be moving at the same time that we move the IPD wheel, the interpupillary distance adjustment wheel, and they are moving symmetrically. So they are moving the two at the same time, either this way, opening or closing. Once you get used to this interface, once you understand this, everything is trivial. You will see that as soon as you move the IPD, you will see that the small spots will be either entering or going out. And that's all. Also, in order to take a measurement, you don't need the eyes to be exquisitely aligned with the device. Okay, there is a range in which the device works perfectly. And one of the reasons is because, again, we are acquiring in video mode. During the measurement, the eyes of the patient are slightly moving. Okay, and that means that the spot diagram is in different positions of our screen. That means that our algorithms can take advantage of the situation in order to extract all the information we need to provide an accurate refraction.
Okay. There's a question of how do we know that the patient is looking correctly instead of at the dots, they're looking at the distant target?
So basically, in order to ensure that, especially with children, we use tricks. The typical thing is I use the device in conjunction with a visual acuity chart or a target that is at a certain distance, something like 4 meters. For example, if the patient is looking at a visual acuity chart, when I start the measurement, I start to ask the patient, okay, can you read me the second line? Or can you read me what is written in here? And the patient starts to tell you is A, B, C, whatever. And by that time, the acquisition has finished. In this way, we usually ensure that the patient is looking into the distance and not to the red spots. That will be the answer. This is the typical thing we do.
Now, one of the things that several of our customers have found successful is to put a target that's very engaging for the child. So a poster with animals or cartoon characters and asking them to tell you how many animals they see. That keeps them focused on the target.
Yeah, also I remember some of our customers working with children. They used to have a tablet and they play cartoons in the tablet. And we're asking the kids to look at the cartoons and to tell something. So can you see the bunny? Or some details. It's just a matter of asking about what they are looking at.
Okay, I'm looking through the questions. Let's see if we have, I think we've answered most of the questions. Does anybody else have any other questions? We have a couple more minutes available. There was one question that came in, not sure what they mean, but who suffers from nystagmus?
So in case of nystagmus, so first we have to measure in monocular mode because one or the two eyes of the patients will be having non-standard movements, non-periodic movements, and it's really tricky with any auto-refractor. So to be honest, we didn't have too many patients with nystagmus. I know about one of our doctors here in Spain, which is using with this kind of patients. He told me that he has been able to take measurements always in a monocular way, and that the results are satisfactory. But to be honest, I don't have a lot of experience with this kind of patients. I think that this doctor have seen like 100 of them, but I don't have detailed reports about the performance of the device in this case.
Okay. Yeah, so somebody said if they could get a soft copy of this training. I'm not sure who it is because they were registered as an anonymous attendee. We have all the training material available to our distributors. I will make sure that after this training session, you will all get a copy of the training video, the webinar today. And then I will also provide you with the contact details of our distributors, and they have all the training material. There is a question that came in, patient with ptosis.
Again, any kind of problem limiting the amount of light going out of the eye will create problems. But in this auto-refractor or in any other refraction system in the market. So in general, auto-refraction or always auto-refraction works by putting light in the eye of the patient and measuring the light that goes out. In this case, the performance of the device will depend on the magnitude of the problem. It will be cases in which the patient can be measured, and it will be cases in which it will be impossible to measure the patient. Depends on the magnitude of the problem. It's the same with a cataract, for example. In some cases, you can still measure accurately the patient, but in cases in which the cataract is in the middle of the pupil or is very big, the device will have problems and may not be so accurate in those cases.
Okay. Let's see, we have so it seems that we have a customer that is concerned that she's unable to use the QuickSee device always in binocular mode. My sense is that when she received the training, that might not have been covered effectively, or it was covered insufficiently. Can you give her an overview, Eduardo, why for certain patients you have to do it in binocular? My experience is typically about 80% of patients we do in monocular. We also now have the sequential single eye software that makes that workflow from binocular to monocular very easy. But could you give them an overview?
Yeah, first, this is related with experience. Okay, I will say that I am able to test more than 85 or 90% of the patients in binocular mode. But some of my optometrists or engineers, in some cases, they have problems. And there are certain things. So first one is, apart from the left-right alignment of the channels, there is a small degree of freedom that is up-down. Okay, so the first thing that I always check, if it is difficult for me to align in binocular mode, maybe that is because a misalignment up-down. It can be a little bit like this. So the device is designed to minimize this, but most of the times a small adjustment of 1-2 millimeters up-down help on this sense. There are also cases in which the patient has a non-symmetric face. Okay, so for example, imagine that the nose is not symmetric, or that some facial feature is not symmetric. In those cases, it's very difficult to measure binocularly because the optical channels move at the same time, okay, move together. Okay, so we are expecting always the same distance from the center to both eyes. If that is not the case, the easiest thing is to measure monocularly. But that can be done while the device is held in front of the patient. So I press OD to measure the right eye. And after I finish, I press OS, adjust a little bit the IPD, and measure the left eye. Okay, this can be, it will take 10 more seconds. Well, other cases in which it's not possible or it's not easy to measure in binocular mode, if the patient has strabismus or some degree of strabismus, this is also going to affect how easy it is to measure binocularly.
Yeah.
Other thing, the last one, is if the patient is relatively old. Okay, elder people usually have very small pupils. Okay, and also they used to have a not very symmetrical face. So if you put everything in the same equation, in some cases, it's much easier to go directly monocularly than to measure binocularly. So this will be dictated in most of the times by the experience. For example, in my case, just looking at the patient, I usually look at the size of their pupils and their face, but this is something that I am doing by default. And I will know if it is easier to go binocularly or monocularly directly. That is something that will give you the experience.
Yeah, I think thank you, Eduardo, an important thing to mention is that the device was specifically designed to perform measurements binocularly and monocularly.
Exactly.
And in fact, we have a new software, the sequential single eye, that allows you to start with a binocular measurement. And if for whatever reason you can't, it automatically channels you into two monocular measurements. There are going to be patients where you will never be able to do a binocular measurement. So as I said, from my personal experience, about 80% of the time, you can measure patients binocularly. When measuring a patient, I would go through that process that Eduardo said, the pupil size, strabismus, amblyopia. I would ask the question, do you have a cataract? I would see that they have a droopy eyelid or an asymmetrical face. And those patients, for an extra 10 seconds, you just end up doing two measurements. Now, what's very important is you are not losing the ability of the open view of that measurement. So you don't, the open view is associated with both the binocular measurement and the monocular measurement. So the results that you get are equally as accurate. You're just doing them one eye at a time.
Yeah, just to mention a little bit more about this. So I remember also one of our customers that was having problem in measuring binocularly one patient. And the problem was that the patient has a big cataract in one of the eyes. How we realized about that? We went into monocular mode. We measured first the eye that was easy to measure. And with the other eye, we went into a spot diagram and we see very clearly the cataract and say, okay, this is the reason because we cannot measure binocularly this patient. Okay,
Yeah.
Yeah,
and that's an interesting point that the Shack-Hartman point diagram is only available in monocular mode. So that's why you have the ability to go from binocular to monocular and look at that additional data. Okay, I'm going to field one more question. The question came in, how do you measure a patient that cannot focus and an image that's too far?
So if that is the case, so that means that the patient has myopia, and usually the thing that we say to him is look into the distance to the farthest point that you can look at, and that's all. That's all. This accommodation problem is important with young people, but with people with in their 40s or a little bit more is starting to be much smaller, and this is because of presbyopia. The smaller the capacity of the patient for accommodating, the smaller the problem, and also this is something that happens in any refraction device. Okay, but in our case, because of the open view, we are highly mitigating this. Okay, that would be the case. Even if the patient cannot focus on a distant target, we just ask them to try. And for example, if you are using a visual acuity chart, if the patient cannot see the smaller line, you can always ask him or her, okay, what is the smaller line that you can see? Is this one? Is this one? Can you read it? This is the way we proceed.
Yep.
We proceed with the device.
Okay. Edu, for strabismus, would you cover one eye or block one eye for the examination to take up fixation, or would you just do the 2 monocular measurements?
I will let that to the criteria of the optometrist. In this case, both situations are possible. And it depends on the optometrist. In this case, some optometrists prefer to do A, some optometrists prefer to do B. Both things are completely possible in this case.
Okay. So I will take one last question. We've already been here for an hour and a bit. We still have a lot of people in attendance, so thank you very much. Clearly, it was an interesting topic. So if there's anybody that has one more question, please submit it now. I'll wait 1 minute, and if not, we'll just complete the presentation. I will be sending everybody a copy as well as the link to the corresponding distributors in each country. We have Rana Diab, who's giving us a compliment. Thank you very much. They did more than 4,000 patients. Very happy with the device. It works very well. They were testing children, which they accommodate a lot. QuickSee relative to other auto-refractors gave very accurate results, reducing the overall accommodation effect. So thank you very much.
Thank you.
Okay, thank you, everybody. Really appreciate your attendance. And as I said, you will be receiving all the material.
Thank you very much to everyone.
Okay, thank you.
Thank you.